This is Tian from Growth Lab. Today I will share with you my experience adding custom vector instructions using Sail. This is today's agenda. I will briefly introduce the Sail language and the Sail tool. I'll talk about the current status of Sail for RISC-V and explain why we use Sail. Then I'll talk about our goals, some of the challenges we've been through, and some of the tool limitations that we'd like to bring up. Sail is a language for describing instruction set architecture semantics. It defines the instructions assembly and disassembly, binary encode and decode, and also semantic. It is an engineer-friendly pseudocode-like language. It supports lightweight dependent typing for numeric types and bit vector lengths. For example, you can declare a 32-bit bit vector type using bits 32. Given the Sail definition, the Sail tool can do type check, generate documentation in our text, generate executable emulators in C and OCaml, generate random generators for testing purposes, generate theorem prover definitions, and generate definitions for concurrency semantics. Sail is being used for multiple instruction set architecture descriptions, including RISC-V. It supports primary extension RB32i and RB64i, and standard extensions such as multiplying divide, atomic, compressed, and floating point standard extensions such as single and double precision. It supports interrupts, counters, and timers. It supports machine level and supervisor level instructions, and physical memory protection. It is complete enough to boot various operating systems. Normally, when we develop a new instruction set, the description of instructions, the function model, and hardware implementation are all evolving at the same time. A lot of times, both function model and hardware implementation have bugs. Even the description of instructions written in English will cause ambiguity. Therefore, defining the instruction set in Sail language will help remove the ambiguity, and the Sail tool will generate a golden function model for reference. This is an overview of what we're trying to do. There is a vector pipeline attached to the original RISC-V pipeline, together with a vector rich file. There are some differences between the vector instructions and the standard RISC-V instructions. The vector rich file can be used to represent different element sizes and variable depths. And the vector instructions supports multiple data types, which is selected by CSRs. Our goal is to define the customized instruction set architecture extension Sail language based on existing RISC-V Sail. We would like to generate a golden C model, documentation, and random texts using the Sail tool. Also, we would like to leverage the C model generated from the Sail tool to our performance model in our test bench code simulation environment. We treat this C model as the only golden reference. Thus, all the implementations such as the performance model and RGL must match this C model. Now, let me talk about the two major challenges we've been through. First, how to implement vector registers with variable element sizes and depths in Sail. Second, how to implement instructions that support different data types. For the first challenge, there is a vector type provided by Sail language already, while it is fixed in depth and width but declared. So we implemented a set of wide scalar registers and dynamically cast into vector registers based on the data type using split and join functions. When implementing the split and join functions, we hit a Sail bug with type checking, which is resolved by the Sail team. Here is an example. Vector registers are implemented as scalar registers with bit vector type called v-ret type, rather than the vector type. The split function takes that, the width, and the bit vector as input, and returns a vector with a specified depth and width. The resulting vector is built by taking subranges of the input bit vector using the function slice. There is a corresponding join function for writing values back to the vector registers. For the second challenge, one simple solution is to implement one function per data type per instruction, even though they share the same functionality. This is because of the strict type checking for function arguments in Sail. After our discussion with the Sail team, we used a workaround called type variables, which allows us to pass width and depth information into the functions. Together with the split and join functions, we only need to implement one function per instruction for all supported data types. Here is our implementation of instructions that support different data types. Type variables are declared as part of the function prototype. All possible values of the type variables are defined in the function quantifiers. As we can see, the depth and width are inputs to the process DB. This subfunction is required to use type variables. Without type variables, there must be multiple process DB functions, one for each possible width values. Now, I will talk about some tool limitations that we would like to address here based on our experience. First, I would like to talk about the experience for leveraging the C model. Then I will talk about the quantifier checking done by the current Sail and dynamic typing. Lastly, the code generation for verification purpose is not fully complete. I will describe in detail. As mentioned before, we treat the Sail generated C model as the only golden reference, and we would like to leverage the C model and integrate into our performance model and function verification test bench. We are integrated with the existing C model, and we believe there might be some enhancement needed to make the integration easier, such as to not use global variables in the functions, pass values or pointers through function arguments instead of accessing rich file or memory directly inside the functions, and maybe name some key variables instead of auto-generating names for better understanding. Next, we would like to see if the quantifier checking could be enhanced. Sail currently uses quantifiers to determine all possible values that a variable might have. The tool right now is not smart enough to infer the intrinsic range of variable values in certain scenarios. We figured out a workaround by using a search statement, but there might be a better solution. In this example, the code generates the log2 of the element with bits. Possible values of within bytes are defined in the function prototype, which are 1, 2, 4, and 8. A match statement defines all the possible values of log2 bits based on all the possible values of within bytes times 8. But the search statement, which defines the range of log2 bits, is still required to compile. Otherwise, could not resolve quantifier error will occur. Therefore, we believe the tool can be smarter when trying to figure out the possible value of certain variables. Another limitation is dynamic typing. Real-time spec allows to change text length dynamically, but current Sail cannot support it because 32-bit vector and 64-bit vector are different types, even though they share most of the functionalities. But custom vector registers using type variables and split join functions is just a workaround in order not to repeat the functions over and over again. Type variables are not true dynamic, since they must be declared with all possible values in the function prototype. One cannot calculate the size or depth inside the function. I know that this is kind of against the rule of strict type checking of Sail, but if there can be any enhancement, it will help with the user experience. Lastly, Sail Ocamo backend can produce quick check style random generators for types in Sail specification, which can be used to produce random instruction sequences for testing. But for hardware verification purpose, the random generators need features to control opcode distribution, to create fixed opcode sequences, to control data dependence, and most importantly, to inject errors. These features will boost the coverage of the tests and make the tool more useful. In summary, today we did a brief introduction of the Sail language, the Sail tool, and current status for supporting RISC-V, and explained the major reason for us to use Sail. I talked about our customization goal, challenges, and some of the tool limitations. That concludes my presentation. Please let me know if you have any questions. Thank you.
So, thank you, Tian. Do we have any questions regarding the sales model or project itself? Okay.